Okay, so welcome back to Math 110. So we're going to start, I'll just throw this out there. The first roughly 2 weeks is pre-calculus material, I would call it. So it's should be a lot of review. If you took Math 22 at Penn State, you probably saw most of this or all of this, hopefully. And you've probably seen this at the high school level. So we're going to talk about functions in section 1.1. It's a rather lengthy section. There's a lot of information in it. So what I usually do is leave a little bit out until next time. So we're going to go through most of the information, but probably not quite the whole section today. So we're going to define a function. Before we do that, I want to just somewhat define a couple terms that hopefully you're familiar with. The first one is set. And I'm not going to put any formal definition down. It's actually kind of a difficult word to define because you're really just exchanging another word like it, like collection or a group. A set is, if there's any word that defines itself, it would be set. And usually if you see some, set diagrams, Venn diagrams, they call them, it's usually a circle, but I'll just make it as a blob. And if we name some set and call it A, this is A, this is a set, and the sets that we deal with are going to be numerical, typically the real numbers. Those are the numbers that reside on the real number line, and it could be just a portion of that, numbers from 0 to 1, or anything. It doesn't have to be numerical. We could have a set defined A. It could be the students in this class. It could be the cars in the Walmart parking lot right now. Whatever you want. You can define a set however you like. And then the individual components are what we call elements. They're elements of the set. So if your set is the cars in the Walmart parking lot, each individual car is considered an element. So this will help us define a set. So I use a lot of abbreviations. So when you see this is DEF, this is definition. And it's kind of a lengthy definition. It actually defines multiple terms in one. So we're going to go through it very deliberately. So a function. And for this definition, I'm going to call it F. It doesn't have to be F. You could call it whatever you want. A function F is a rule. Okay, what does it do? That assigns. So it's some sort of rule that's going to assign something to something else. A function F is a rule that assigns some element, an element in a set, which we call the domain. Called the domain. So we're actually sort of defining the word domain in here as well. So it's going to assign an element in a set called the domain, and I'm going to leave a space here for a reason. So the English might seem a little broken up because I'm going to fill this blank in a minute. I'm going to assign an element in a set called the domain. Element. So you should think it says, well, to an element, but we're going to have some precise wording here. An element in a set called the domain to an element in another set that we call the range. So two sets of interest here. So the typical sort of diagram might look like this. I'll use these blobs again. This is going to be my domain. Oh. these are my inputs. Okay, I have another set over here. And this is my range. And say that's some arbitrary element. I'm going to hook this guy up with an element over here via some rule. That's called my function. Okay, so I'm going to come back to this. This is a sketch pad, so I have to flip back and forth a little bit. So an example and another abbreviation example. Let's use the car example. So these are cars. This is my domain. And I'm going to say these are the cars. I'll just say lot. It doesn't have to be Walmart. Make some dots. A bunch of cars. All right, I did 6, but we'll just pretend there's a lot. It doesn't matter. And let's have this set over here. This will be called, this is the range. And these are the colors of the rainbow. So these are colors. So what I'll do is I'll assign each car to a color by the color of its interior. So I go out and pick some random car, look inside, it's got a white interior. Well, this function is going to say this car goes to white. It seems kind of silly because it is. Like I said, we're going to work with numbers, so it'll be a little less abstract. But I want to go back to the definition because we left something out. So this idea is pretty straightforward. You got 2 sets and you're going to connect them via some rule. And think about these, this should be thought of as the inputs and these as the outputs. Okay, so what did I leave out up here? We're assigning an element to another element, and the key part of being a function called the domain to not just an element but exactly one element in a set called the range. So what that means is that given an input, the output is unique. There's no negotiation. There's no room for artistic interpretation. If I go back to this example and I go pick out a car, I don't say, that interior is white or it's off-white. No. There's one answer and there's one answer only. Okay? That's what makes a function a function. Every input has a distinct, non-negotiable output. And just to see this, let me clean this up. So this is a non-example. What I'm going to do is I'm just going to flip-flop the sets. Now I'm not going to use domain and range because this isn't really a function, but I'm going to say, all right, over here this set is the colors now, and these are the cars. Get some dots. And then this rule, I'll take a color, and then that color will go to any car of that color. So the color white could be assigned to 20 different cars. That color does not have a unique output. So this is not a function. Okay? So I'm going to try to keep the speed appropriate, but of course you can pause and rewind and fast forward, whatever you like. Okay, so that's a definition. No, I don't ask you to repeat definitions on exams, but you got to know what things are. Okay, so some notation. This is function notation. So this is a very standard kind of a diagram. What I'm going to do is I'm going to represent the function here as a box, like a machine almost. And I'm going to take an input. So this input I'm just going to call x. I could call it whatever I want. And this, of course, is from the domain. And that element will be input into some function, and then I spit something out. And this is the notation that is used, and this is read as f of x. And this, of course, would be in the range. This is an output. So this is not f times x. This is not f, whatever. This is one block of notation. It's read f of x. This is what you get when you apply f to x. You get something called f of x. And we're going to use this notation to define our functions. So how do we define functions in calculus? So let's call this function definition. Now when I say function definition, I don't mean the definition from page 1. I mean how you define an actual specific function. Definition. And we'll do it this way. And I'm going to stick to the same letters. And again, we don't get married to these letters. The letters can change, and the book changes them up quite a bit in the exercises. But we're going to try to stay consistent here at the beginning. So we'll define a function this way. We're going to say, okay, this function is going to be called x. I'm going to see this. This would be what would be considered the output. And this will be the input. So I'm going to say the output in terms of this input, the output in terms of this input is equal to something. So this, what's on the right, will define this function f. And maybe let's keep this simple. Let's just say whatever x is, and we're going to get away from the car thing now. I'm going to take my input and I'm going to add 2. So this is my output. And of course, if these are equal, these are the same. So this is my output as well. So f of x is the output. X is the given input. Sounds like I'm going in circles here, but what's on the right defines the output in terms of the input. So I'll use this same example. Having defined this function, x plus 2, well, what could we do? Well, if this is the definition, I might say, well, what's f of 1? Well, 1 is my input, so 1 is replaced on the right-hand side. So this would be 1 plus 2, which I still believe is still 3. What's f of, say, negative 1? Negative 1 is now the input. The output is negative 1 plus 2, and that's 1. They don't always have to be numerical. Okay, so this is where sometimes people get a little confused. How about, let's say, f of a, little a. What's little a? Who knows? Who cares? It's my input. Someone's telling me that that's my input. So my output is a plus 2. What's a plus 2? Who knows? Who cares? So this hopefully is straightforward. This, what I'm about to write, I'll squeeze it down here, is a little more understandable where the confusion comes in. Because now this input has an x involved. But I still just think about it very crudely. Whatever's in this set of parentheses is my input. In this case, it happens to be x plus h. So x plus h goes in for the input on the right. X plus h has replaced x. X plus h replaces x. So x plus h plus 2. And this seems maybe like silly, but this is actually going to be quite useful down the road. And it's a source of early confusion with some students. So make sure, take a good look at what you see right here. Just think of it this way. What if I said, well, here's my function that I've defined. What's What's f of smiley face? Well, smiley face plus 2. Okay. So think about it very crudely. Just take it at face value. Don't overthink it. And hopefully, I'm sure you've done some of this. So what else do I want to say about that? I guess I'm good there. One thing that we'll do, and there's an airplane flying over the house. One thing, I lost my train of thought. I want to just touch on something that I'm sure you've got familiarity with, and that's we often represent functions graphically. So I'm not going to spend a whole lot of time on this because I know you've done it, but I want to address something on the past page with this. And we work in 2 dimensions in this course. So x and the inputs we find on here, and then they are projected to an output vertically, which we call x. So just for the record, and don't get too hung up on this, if I go back to that function, that graph would look like this. So if I go back here, f of 1 is 3. That's my 1, and that's projected up here to 3. And we represent these as coordinate pairs. That point is 1, 3. The graph is the set of all points possible from the function. One thing I want to go back to is, what if I do this? I like this. This is good. Let's say y equals x plus 2. So you probably recall mx plus b form, so on. And then my question is, well, is this a function? Well, I know the graph looks like this, right, from my mx plus b stuff. And your quick answer could be, well, no, it doesn't have this f of x. Well, that's not true. You don't have to represent a function with this notation, and sometimes we won't. It's a function if that original definition applies. So quite often, y and f of x are used interchangeably. Now, the good thing about this notation is when you see it, you know you have a function. You also know exactly how we're defining the input, because I could write f of x equals x plus c. Well, you see 2 letters on the right. How do you know which one's the variable? Well, whatever's in the parentheses is the variable. So that's a nice part about this. And what I'm getting at is, if you see this, just y and x, is it a function? Maybe, maybe not. Why? How do I know that? Because this has a y and an x, and this is a circle. And this is not a function. This is what you'd call a relation. So when it comes to graphing, there's the old, test, trick. We call it the vertical line test. And this goes back to the definition. What this says, and I'm going to point to these graphs. Let me write it down first. How do I want to word this? Let's word it like this. Every possible, which I guess that's kind of redundant, every possible vertical line may intersect the graph of a function I'm running out of room. At most once. You can cross the graph once, and it it can cross 0, but once is the most. At most once, not twice, not 3. So the way, this is just a kind of a mental exercise, like I look at these, the first two, we know those are functions. I think about cycling a vertical line. Like this is going to be every possible vertical line, and I can see that the pen is crossing that line once. Excuse me. As opposed to the circle, where if I cycle that through, I'm hitting it twice. And that goes back to the definition. Up here, every input is going to one output. Every input is going to one output. Down here, I got this input, it's going to 2 outputs. No good. And again, this would be formally called a relation, but not a function. And this is easy to do, I hope. If someone shows you a graph, you just, it's a quick thing. Is it a function? Now that's not quite as easy if it's algebraic, unless you see it written like this. Okay, so doing good? Okay. What I'd like to do, I want to focus on 2 styles of problems. Let me just check let me check my notes here for a second, what I want to do. Okay, we're good. There's 2 very standard types of problems in the Calc 1 course. Which one do I want to do first? Let's do the domain problem. So this is a problem that we're going to have to be able to do throughout multiple semesters of calculus. Given a function, what is its domain? What does that mean? Well, let's go back here. That means that what is the set of possible inputs? Because maybe not everything goes. Now if I go to my examples over here, the x plus 2, there's no number you can think of that you cannot add to. So everything goes. The domain of this function is all real numbers. It's not always the case. So how do I find the domain? Well, one thing I don't do is try every possible number I can think of and say they're in the domain, because obviously that's ridiculous. But this is what we do. So we actually do the opposite. Determine what is not in the domain. So you're going to pick out the bad apples, right? You pick out all the bad apples, and everything left you can eat. Well, what makes a function a bad, or what makes a number a bad apple for a function, right? What would make a function crash? What would make it an invalid input? And really, at this point, we have 2 things. As you go through semesters of calculus, you'll add other things when you see other functions. But the 2 things that bad apples, I'm not going to write apples. What's bad? Number 1, you cannot divide by 0. Division by 0 is no good. If a number goes into a function and results in the potential of division by 0, which there is no potential because it's nonsensical, but if a number puts a 0 in the bottom, in the denominator, it's no good. And 2 is, and I'm going to leave a space here specifically. I want to put square, but it's a little off. Root of a negative. And I want to say square root, and that's true. You can't take the square root of a negative in the real number system. If you've heard of I or things like that, if you know what that is, that's fine, but that's not the real number system. So we don't deal with I. I doesn't exist to us. But it's not just a square root. It's any even root. For example, in other words, you can't take a fourth root, a sixth root, an eighth root. Why you would want to do that, I have no idea. The point being, you can take odd roots of negatives. For example, the cube root of -8 is -2. -2 times -2 times -2 is -8. We'll mostly see square roots, so I maybe could have put square root and gotten away with it. But more precisely, it's any even root. So this is one thing I should mention right now is exams are, I guess, what they call open response. And what that means is it's not basically it's not multiple choice. You're going to show your work and I'm going to grade your work. So this needs to be established right away. If I'm grading your work, I'm grading what's on the paper, not what I think's going through your head. So first of all, if I can't read it, you get no credit. Everybody thinks their handwriting is great. I mean, I think mine's pretty good, but somebody might think it's terrible, you know. Try to write neat, but it needs to be coherent. It needs to be an argument. You know, we're not doing times tables here. We're doing problems that have involved steps. Those steps need to be shown, and they need to be shown sort of like, think about it like a story almost. Now, it doesn't mean they're all going to be 2 pages long, but you need to show what's going through your head on paper. So one thing I want you to do is to some level, mimic the way that I do the problems. It doesn't have to be exact, but what drives me, and I'll show you what drives me nuts. I'm going to do some domain problems, and there's a coherent argument to what I'm going to do, and that means the person that's going to read it, even if I make a mistake, they know at least what I meant. If it's just a bunch of chicken scratch written all over a paper, they're not even going to know what I was trying to do. So find the domain. So this is I'll do 2 or 3 examples. The problem statement is simply find the domain, which means the real problem is we're going to find out what's not in the domain. So we'll start out. Let's do like an easy one. Here's a function. F of x equals x plus 2 over x squared minus 9. And this one's, you could probably do without much work. You could think through it. That'd be called solution by inspection. But I want you to see what a systematic approach looks like, because you can't always do a solution by inspection. So I think there'll be 2 issues. There's no root in here, so that's a non-issue, but there is division. So there's potentially division by 0. So the statement I'm going to make is I cannot allow the bottom to be 0. Those would be the bad guys. Well, I have a little equation here. We have an equation set to 0. We're going to solve said equation by factoring. We factor to solve equations in calculus. I have 2 solutions, plus and minus 3. They're the bad apples. They're the cannots. They're not allowed in the party. All right, so those are the not domain. So what is the domain? Everything else. And the standard way to show, remember, the domain is a set. If this notation, I'm going to use, it doesn't matter what we call it. It's not a big deal. But we're going to use set notation, and this is a group of intervals. So I'm going to go -infinity to -3. And I'm okay with a comma. This is more formal. That means union. And then -3 to 3. And then 3 to infinity. So really, that's just a long-winded way of saying everything except the bad apples, -3 and +3. If this is bothersome, there's somewhere in the book they lay it out. It's not as complicated as it looks. It's not complicated at all. But if you've never seen it, you might want to check that out. Okay, so again, going back to the problem, let's just think it through. I want to find the domain. I want to find what's not in the domain. This function involves division, so this is a potential issue. I say I can't allow the bottom to be 0. The implication of that is I can't have x be plus or minus 3. The domain is everything else. All right, let's do another one. Let's keep it simple again. Now I'll do one that's more complicated. Real simple here. Square root x plus 2. Alright, this one has no division. This has a square root though. What do we say about square roots? Can't have a negative underneath. I can't take the square root of a negative. So whatever's under this root cannot be negative. In other words, mathematically speaking, it can't be less than 0. That's negative, right? Well, again, this is a little inequality. So x cannot be less than negative 2. In other words, x can be, and this is inclusive, 2 to infinity. I'm sorry, negative 2. Can't be less than negative 2, so it can be negative 2 and up. Why? Because if I'm less than negative 2, I got a negative under the root. It's no good. Let's see one that's got a little bit more sophistication in it. Let me maybe steal one out of the textbook here. My lips are really chapped. I got a little touch of a cold, I think. But that's not your problem. Okay, let's do this. Let me just make one up. This will have some division. Let's say x squared plus, let's do this. Yeah, plus 4x plus 4. Is that going to work for me? Yeah, that's going to work for me. And then on the top, let's just say x minus 6. I don't know. Okay. So why is this a little bit more involved? Because we have multiple issues. So we're going to address each issue individually, and then we're going to get rid of all the bad apples. So the first, I'll do this because it's side by side. There's a root. I can't allow what's under that root to be negative. So I cannot allow x to be less than 6. Okay, so everything less than 6 is gone, right? But I have a second issue. I got division. So I'm going to say, well, that denominator cannot equal 0. And again, I'm going to factor this. This has two identical factors. So in addition, x cannot be equal to negative 2. So what I'm going to do now, and I like to, when I show these, on the board, when we get to class, whatever, you can maybe just do something like this on a piece of scratch paper. All right, x can't be less than 6. Okay, so this is no good. X also can't be negative 2, which is down here somewhere. Well, there's a redundancy here. So this guy gets tossed for 2 reasons. So in the end, I'm going to say, okay, this is good, 6 and up. Okay, the domain problem. Follow the pattern. It's on every exam 1, calc 1 in the history of the universe. Okay, the second problem you could say the same for, and this is a problem that's going to reoccur throughout the next, couple months or 6 weeks. And it's evaluating this wild-looking expression called the difference quotient. And all that means is it has division and subtraction. And you can have different ones. We're going to focus later on a specific one. But in the homework, you'll see different ones, but they're all kind of the same in structure. So let's see. Let me make a simple one up, and then I'll do maybe one or two more difficult ones. But the problem statement here is straightforward. Given some function, let's say x squared plus, that's not what I want to see, my bad. Given f of x equals x squared plus 1. Okay, given this function, well, what? Given this function, we will evaluate some difference quotient. So this is kind of the main one we'll see later. And you say, what is this monstrosity? Well, at this point, it doesn't matter. We just want to get through the mechanics of this thing. So, whatever. So this is the problem statement. All right, so this thing, there's the difference. Well, what is this equal to? So f of x plus h, this goes back to something from the beginning. That is what I get when I put x plus h into this function. So I'm going to use a lot of parentheses when I do these. So that's x plus h squared plus 1. Oop. Okay. What's f of x? Well, f of x is up here. How do I know? Because I can read x squared plus 1. And I'm going to put that in brackets too. The reason I like a lot of parentheses is subtraction leads to a lot of error because people don't distribute the negative. If there's no parentheses here and this is written this way, this is incorrect because this negative will distribute over these two terms. What's on the bottom? H. What's h? I don't know. We'll get to that later. Okay, so I filled this thing out. That's kind of like half the battle. The rest of this is glorified algebra. What do? You're going to try to simplify this. What do you consider simplified? This is the secret. To finish the problem, you want to get rid of the bottom. You want to kill that h on the bottom. So how do I get to that point? Well, we just do what's available. All right, you take what you're given. So I'm going to FOIL this out. X squared. And then I got this 1 kicking around. And then I'm going to distribute him, right? I'll try to slow down here for a bit. And again, you can pause. That's the nice thing about here. Okay, so this thing blew up and got nasty. Well, this is very common. You blow these things up and then they implode on each other. I got an x squared minus an x squared. I got a 1 minus a 1. So 4 of these 6 terms vanish. I hate going this way, but I don't have a choice. So I'm left with 2xh plus h squared over h. And this is the common ending. There's an h in each of these. I'm going to factor it out and then cancel it. There's one left here. Okay, the h's cancel. I've canceled the bottom. I've killed the h. It might not always be an h, but that will be common for us. So the result is 2x plus h. Now, what use is that? At this point, absolutely none. But later, it will be of use. Okay, let me do one that's a little bit more involved. So there's, like I said, when you do one of these, there's two parts to doing it. One is filling the thing out correctly. If you can't get to this thing filled out, you have no chance. And this is where the problem lies. People struggle with that. I mean, this is just copying this, and this is just a letter, right? H. So you get the thing filled out, and then it's just kind of like, an algebraic exercise. All right, let's see another one. Let me see here. Oh, this, yeah. Let me do this one. This might not look too complicated. Yeah, let me do this. So given f of x equals 1 over x plus 1, evaluate, and I'll use the same difference quotient. Okay? Again, the goal is to find a way to kill that h. Okay. Here's my solution. My difference quotient equals, and again, here's the focus. What is the function when I put x plus h in as the input? X plus h plus 1. I could have parentheses around that, but there's no need. Minus f of x over h. So it doesn't look too bad, but now you got this kind of mess up here. And what I'm going to need to do to subtract fractions is get the LCD, our old friend, the LCD, and then I can combine this. So this will have x plus 1, and this will get this x plus h plus 1. So this is x plus 1, x plus h plus 1, all over h. And now I have some cleanup duty at the top. Again, if this negative is distributed, there's minus x and minus 1, so they'll kill these two guys, and we got minus h on top. So let me bring that down. So up on top, we are just merely left with negative h, and then we have these two beauties right here, x plus 1 and h. So you never want to have, well, I shouldn't say never because we don't have a choice sometimes, but you want to have a distinct numerator denominator. This sort of like whatever this is. Looks like a club sandwich kind of, or a hamburger. This is no good. So if you got stacked fractions, you flip the bottom, right? Multiply by the reciprocal. Well, you might say, well, this isn't a fraction. This is just an h. Well, anything can be thought of as a fraction if it's over 1. It doesn't have to be that I don't have to write that, but you can always think of it that way. So if I flip the so-called bottom, then I can have a distinct numerator and denominator, 1 over h. And there's no reason I can't just have that. I shouldn't even have him there. And now the h's will go away. Now I still have stuff on the bottom, but that's okay. The cancellation of that guy, there's still actually an h left in the bottom, but the original one has been eliminated, and that's the goal for reasons that we will get to soon. So these problems, the ones that I'm going to assign they're pretty challenging. Some of them are. Some of them actually I think are a little overkill. But look at these examples. Know the process. I mean, if you do some of these, and some of the, like, it's easy to make an algebra mistake. That's not the point. The point is knowing how to fill this out. Really, this first step is the main point, and we hope everybody's competent with their algebra. But I'm going to leave a few topics out of the section. This is enough for day one. There's more, but like I said, it's a big section, so we're gonna end there. We're gonna end there at the 45-minute mark.